All right, everyone. It's me, Mr. Lee. In this video, we're going to go over the open system. Previously, we did the closed system. We did some practice on it, but now we're going to talk about the open system. But before we begin, let's discuss what makes a system a closed system, because you need to be able to make that distinction. So, a closed system, um, nothing is interacting with the system. Okay, so in terms of the LOL diagram, it is the middle part of that diagram where nothing is affecting that. And now we're about to see exactly why I have you making those energy bar charts, because we will be affecting the system. We will be affecting that middle part of the energy bar charts. Okay, more importantly, closed system, there is no friction. Okay, and there is no air resistance in these types of system. Now, another term that I want to remind us of is the term mechanical energy. So mechanical energy comes in two forms. It is potential energy and kinetic energy. Anything else is not considered to be mechanical energy. Okay, and so when we talk about an open system, we will discuss how the mechanical energy of the system might change. Okay, and so up until this point, we just called it the total energy, but it's important to make that distinction that total energy of a system can adjust because the mechanical energy does change. All right? Okay, let's do this. Yeah. So first thing, let's go off with a definition. And we can just start off by going against what is a closed system. So an open system, we can say that your mechanical energy initial, so your potential and your kinetic energy, does not equal to your mechanical energy final. Okay, so something has changed the types of energy along the way. All right, and so what this tells us is that energy is taken away from the system or added to the system. And we'll see the distinction between the two. Now, this here is a very important definition. When energy is taken away or when energy is added, put a little star next to that one is so important. It's one of the fundamental parts of our entire course, our entire universe. This definition is the definition to something that we call work. Now, you might be familiar with the idea of work, like homework, classwork, doing chores, going to work, and all that. But for physics, work is when you're either adding energy to a system or when you're taking energy away from the system. Okay. Now, there's other definitions for work, but for the sake of this video and for the sake of us being able to do the different kinds of problems that you might see, that is the definition that I want you to stick with. All right. So that is the definition of work. Yeah, let's go into like an example of how energy is taken away or added. One of the things I told you about the closed system is there is no friction. Okay, so if we were to have friction in a system, okay, we can say that friction takes away energy. Okay, and more specifically, it takes away kinetic energy. It slows it down. So what friction does, okay, friction does negative work because the energy is taken away. So you're either adding energy or taking away. And if there's friction, there's negative work. All right. So with that example, I want us to start off with our very first example here. 1. Now, as we do this, I want you to leave a little space somewhere in between each problem because we're actually going to go back to it and we're going to add to these examples at the very, very end. So the first one is block slides to the right. Let's just give it a velocity of, we'll make it simple, 3 meters per second. And comes to rest. Okay. And for these type of problems, it's very important to identify what the system is. Now, more often than not, the problem will tell you what the system entails. So I will tell you that the system will just be the block. Okay, it's just the block, nothing else. Yeah, and we'll say the block has a mass of, make it simple for us, 2 kilograms. Okay, so the situation to solving these problems are always the same. You first want to start off with a drawing, okay, a before and after drawing. So here is my block of 2 kilograms. It's moving with the initial velocity of 3 meters per second. Right, those are my velocity arrows. It goes pew 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 pew. Right, with some displacement. We don't know what it is yet, but eventually it comes to rest. So that 2 kilogram object comes to rest of 0 meters per second. Okay, so that is our sketch and our drawing. And good just habits in general. I want to identify the types of energy. So here, the type of energy is kinetic energy. And at the end, because our velocity is 0, and because we don't have a height, there is no more energy. Okay. Now, because there's friction, whenever there's friction, I always like to make the surface a little bumpy. Okay, just as a visual reminder that friction does exist. All right. So the very next thing that we got to do is we got to create our energy bar charts. And until you get used to this, I do suggest that you go from left to right. Okay. So the type of energy that exists initially is the kinetic energy. Okay. So kinetic energy and total energy. Or excuse me, mechanical energy. Yeah, our total mechanical energy. And over here at the end, all right, because it's what we started off with on the left, this is also what we're going to start off or end with on the right. And in the middle, I'm going to define what the system is, and the system is just the block. Okay, so in the beginning, we had a lot of kinetic energy, okay, and that equals to our mechanical energy. But at the end, because we're not moving, we don't have kinetic energy. We do not have any kinetic energy or mechanical energy. And so the question becomes, what happened to that energy? And that's where the middle O comes into play. Okay? So that middle O tells us that energy left the system. Okay, we lost energy. And we lost energy due to work, due to friction. Okay? Now, the energy bar charts will help us out when it comes to our formula. The left-hand side of the formula comes from the variables here, this KE. And the right side of the formula also comes from this KE, okay? And that middle O, you can think of that middle O like your equal sign. But now we're gonna add a slight little twist. What I want you to do is I just want you to do like a dotted line, like diagonally like this, okay? And that dotted line shows us that this arrow where the work is or the energy leaves the system is on the right-hand side of the formula. Meaning, if we were to come up with a mathematical model, we would write it like this. We would write the kinetic energy, okay? Remember that middle O is like an equal sign, is equal to the work due to friction plus the final kinetic energy. Okay, now I know it's 0, but I want to put that in there so that later we can show that we have no final kinetic energy. Okay, so from here we can just plug in, or let's do our variable form first. mv squared is equal to the work due to friction plus 1/2 mv final squared. And at this point, we can cancel out the things. So our final velocity is 0. So our formula becomes 1/2 mv squared is equal to the work due to friction. And at this point, you can plug in the numbers. 1/2 times 2 times 3 squared equals the work due to friction. And that gives us a total of 9 joules. So the friction, the work due to friction took away, so work due to friction took away 9 joules of work from the system. Okay? And if you compare this to before, where we didn't have any work or we didn't have any friction, we would know that the initial energy mechanical and the final energy mechanical, they would have to be equal. But now, because things are more like real life, where friction affects things and different kinds of work affects things, now we're able to set up a formula a little bit more advanced, but basically the same ideas and the same premises. All right. So that will be that. Leave a little space after this because we will come back to it. But we're going to try a different example. So this is going to be number 2. All right, so number 2, we will say a block at rest is pushed across a surface until a velocity of v final is reached. All right, I'm going to define the system. The system is just the block. Okay, and also important here, consider no friction. All right. So when they say no friction, that means energy is not lost. Okay, we don't lose energy, or there is no negative work. So that's my situation. I want to sketch it out. Here's my block of M. Here's my person pushing it, right? But our initial velocity is 0, so I'm not going to draw those speed arrows to show that it's going pretty fast like this. Pew! Right? Yeah, it's moving fast. And to show that this person is really pushing it, right? That's their feet, right? They're running. They're pushing it really, really hard, all right? And so our V here is called just V final. All right, so identify the types of energy. So here we have no KE, but here we do have a KE, okay? Now let's come up with our energy bar charts. So we know that there will be kinetic energy eventually. So I'm going to put that there. Like so. Okay. In the system is just the block. All right. Now you might be wondering, well, Mr. Lee, I know that the person is pushing the block. Why don't you put that person in the system? Simply because the problem says the person is not part of the system, right? That's it. The person is not part of the system. The person is just the block. So if we were to do the bar chart, we know that at the end it's moving. There's mechanical energy. So now comes our formula. Actually, before the formula, let's do that dotted line. And now we have to think. In order for the system to gain energy, because here it gained energy, right? Because it went from no energy to some energy, we must have put energy into the system. So we're going to draw an arrow that goes into the system, and we're going to say work done by the push. Okay, so this becomes your formula. Remember, everything on this side is on the left-hand side of the equal sign. So we can say K plus W push is equal to K. And that's it. So with this formula, we can do 1/2 mv initial squared plus the work of the push is equal to 1/2 mv final squared. All right? And you could plug in your zeros because you know that it initially started from rest. And so we can say the work of the push or the work of the person is equal to 1/2 mv final squared, right? Whatever that number might be. So the kinetic energy, so this is an important part here. I'm going to type this out. There we go. The work done by the person turned into the kinetic energy of the block, right? So if this were FRQ and this is like a statement as part of the FRQ, right? That's something that we should put there because it, allows us to actually understand what's going on with the situation. All right. So once again, leave a little space because we're going to be coming back to this distinction. The first situation, we saw how energy left the system. In the second situation, we saw how energy was added to the system, and the energy came from the outside force. You know what? I'll also put that there. Uh, Energy slash right, which is the work, was given to the system by an outside force, right? And the outside force was a push from the human. Okay, so whatever this person ate for breakfast, it gave them enough energy to push this block. All right, so that's a pretty good statement right there. One of the better ones I've come up with. All right, so leave some space because we will come back to this problem with additional info. Now let's do one last one before we update the problems. This will be number 3. Block on ramp slides down a ramp. Okay. System, consider the system to be just the block. All right. So the system is just the block. Here we have the ramp. Here we have the block, okay? And it goes pew, and it comes down the ramp. So here, we know that it starts at a height of h, okay? But our velocity here is 0, and here our height is 0, but we do have a final velocity of, I'm just going to call it v, okay? And let's show that it's moving. I'm going to draw my speed arrows right there. All right. Now, let's create the energy bar charts. Once again, it is just the block. Now, there might be some of you that are tempted to put the Earth in there, but you cannot put the Earth in this situation because the problem specifically told you that the Earth is not a part of this situation. It is just the block. Now, if there was friction, well, we won't get into that, but it's just the Earth. Excuse me, it's just a block. The Earth is not a part of it. So here we can see that there was a height. So there was an opportunity for potential energy. Okay, we know it's moving, so there's an opportunity for kinetic energy, and that's your total mechanical energy, like so. All right. In the beginning, we have no potential energy. And if you're wondering, wait a minute, Mr. Lee, why is there no potential energy? Let's put this down. UG is non-existent if Earth is not a part of the system. Okay, so the reason why I put that there is because I know you're going to draw this like this and you're going to label it as like an H and you want to put down the U there, but here's a huge point right there. Okay, the gravitational potential energy does not exist if the Earth is not a part of the system, and the reason for that is because UG is equal to mgh, and that g, that acceleration to the gravity, that's that gravitational field variable that we were talking about, right? So if the Earth is not a part of the system, we can't store energy in the gravitational field. All right, so here we start off with no gravitational potential energy. We're not moving, so there's no kinetic energy, and therefore there's no mechanical energy. But at the end, yeah, we're moving, okay? We still don't have any gravitational potential energy, but we do have some amount of mechanical energy. So now you got to ask, okay, well, how do we gain this energy? So first, we gained energy, right? So I'm gonna draw an arrow so that it shows that we are gaining energy. What gave this system energy? So if you really think about it, right, what can bring the object down? and that is, in fact, the Earth. Now, I need to make a huge distinction here. Okay, so by the way, so work done by the Earth. The system, if you put Earth in the system, the Earth can't do work. I'll type this out. This is that important. Earth can do work on the system because it is not a part of the system. If Earth was a part of the system, then we would have gravitational potential energy. Okay, so that's a huge distinction. Because the Earth is not part of the system, the Earth can do work on the system. Versus if the Earth was part of the system, we would just call that gravitational potential energy. Okay? So with that statement being made, let's just come up with the formula. Okay, I'm going to draw it right here. We would say the work of the Earth is equal to the kinetic energy. Now, this was the lab that we first started off with the toy cars on the ramp, right? We released the toy cars and we saw that your starting energy is equal to the kinetic energy. It's all coming full circle, right? So at this moment, I want to make a huge pause here, and I want to compare this system to a closed system, okay, where the system is. Move this over here. The system is the block and the Earth. So if we have a block Earth system, okay, U, K, M, E, U, K, M, E, we would say this object started off with potential energy and it started off with mechanical energy. Okay, and that's because it starts off here with the height. And as it slides down, that potential energy turns into kinetic energy until it reaches the bottom, where at the bottom, it no longer has potential energy, only kinetic energy. Okay, so this is our closed system, because nothing else is interacting with the object. Okay, the Earth and the object is all part of the same system, and nothing else is affecting it. Therefore, it's closed. But here, this here is an open system because the Earth is not a part of the system, and therefore the Earth can interact with it. And so, if we take a look at the formula that we can come up with here, we would say UG is equal to KE. Okay, and we can also say that UG is equal to MGH is equal to, I'll just leave it as KE, right? And the reason why I'm not putting the rest of the variables for kinetic energy as 1/2 mv squared is because I want to make a point here. At this moment, we can define work. We can come up with the formula for work, right? So here is the derivation for work. If we take a look at this and this, okay, because we know that KE is just KE, we can set the KEs and substitute it into each other. And so if we do that, we can see that work of the Earth is equal to MGH, right? Those two are equal to each other if we set these two equal to each other. Now, let's break this down. mg, this is just the force of gravity, okay? And this h, that h is the distance that this object falls down vertically. And that is what we call the displacement. So the work of the Earth is equal to the force of gravity, because that's what the Earth does. It exerts a force of gravity times the displacement that it exerts. So this helps us come up with the final formula or the final derivation of work, where work is equal to the force times the displacement. Okay. Now, this formula has a giant caveat. And on the formula sheets, you won't necessarily see it in this fashion. You'll see it written like this: F delta x times the cosine of theta. And what I want to do is I want to describe to you what this cosine of theta represents. Okay? And this is how we're going to work our way backwards up. So if you take a look at this diagram here, and if we were to draw a free body diagram for the block right there, okay, let me get rid of my little dotted lines, I would draw FG going down. However, if you think to yourself, wait a minute, Mr. Lee, I thought that the object went down the ramp, right? It went down the ramp this way. And so the displacement, what the cosine theta tells us is that the force, so I'll go back here. So this tells us that the force and the displacement must be along the same axis. Okay, so that's what the cosine theta tells us. That's what the cosine theta tells us. The force and the displacement must be along the same axis. So if we take a look at this diagram here, we can see that this object is moving at an angle down the ramp. But if we break down that angle into its x and y components, right, if I were to just do a quick little resketch here, so that's the block, this is the force of gravity, okay? We know that the object is going this way overall, so this is our I'm going to just call it the L for the length of the ramp. That L can be broken down into its components. And those components are the vertical components is going down a height of h, and is also going right of delta x, right? Or a change in the x position. So this h is like a delta y. So in order for it to go down the ramp, it has to go down the ramp and to the right. But what that cosine theta tells us is that only this vertical component is affecting the energy of the system. Because the force of gravity is along the y-axis, that must mean that only the vertical displacement matters here. This delta x has nothing to do with the energy given by the Earth. So we can say here, Fg, okay, and the h is equal to, so I guess it will be, if we're using the formulas correctly, right, work is equal to force times the displacement times the cosine of theta, okay? We can say that the Fg times the height is equal to the work. Now, if you're wondering, where does that cosine of theta come from? Okay, it comes from this angle here. This is our theta, and the cosine is the adjacent side. And so the adjacent side is the height side compared to that angle, right? So that's where that cosine theta comes from. So this is the work done by the Earth. Check. Now, what about the work done by delta x? Well, if we were to have a correct statement, we will say if W is equal to Fg times delta x, as in, put up here quotes, the horizontal displacement, okay, because that h is the vertical displacement, right? We can say that this is equal to 0 joules because the force of gravity is along the y-axis, but this delta x is along the x-axis. Oops, I keep on writing one delta x, but that should just be x, okay? If these two are not along the same axis, your work will always be 0 joules. And that is the work formula. So with that being said, let's go back into our previous problems to see why certain situations add work and certain situations take away, or excuse me, certain situations add energy and certain situations take away energy. So this is problem number one. In problem number one, We have, let's just do a quick little free body diagram for the object. This is the object, f of n, f of g. Because the object is moving to the right, okay, that's our displacement. Our delta x, or excuse me, our f of f is to the left. Okay, so let's take a look here. We said that the friction, we said that the work due to friction takes away energy. And the reason why it takes away energy is if you take a look at this displacement vector, right, which I represent as a velocity, this is going to the right, but this f of f is pointing to the left. And so because that f of f is pointing to the left, it is not helping this object speed up. So here we go. Now we're talking about speeding up and slowing down, because force is mass times acceleration, and acceleration either tells us if we're speeding up, okay, and if you're speeding up, your kinetic energy increases, or it could tell you if you're slowing down. If you're slowing down, your kinetic energy is decreasing. So if your kinetic energy is increasing, that means your work has to be positive. If your kinetic energy is decreasing, that means your work has to be negative. All right? And so if we're moving to the right, so a positive velocity, so here our v was positive, but our acceleration is to the left, okay, so our acceleration is negative, positive velocity, negative acceleration, here we have a slowing down situation. And so because we're slowing down, our work, therefore, is negative. And also, if you want to take a look at the formula, okay, this theta, so if this is our displacement vector, and here this is our force vector, this angle right here, this is 180. Cosine of 180 gives you -1. So that -1 shows us that here we will have negative work. All right, so we can say in a statement, we will say force of friction does negative work on the system. Okay, but more importantly, let's take a look at f of n and f of g. F of n and f of g do 0 work for the system, meaning that f of n isn't adding energy to the system, and f of g is not adding energy to the system, primarily because, here's a big distinction, f of n and f of g have a net acceleration of 0, right? So it has a net acceleration of 0, and so if you're not accelerating, you're not speeding up, you're not slowing down, therefore you don't have a change of energy. Okay, and also, if we take a look here, our displacement is along this x-axis, but this f of n is in the y-axis, right? So f of n is y, our displacement is x, and you have to have the two vectors in the same axes. And if we were to go to this formula over here, right, we said that that Ke is equal to the work done by friction. Now we can have a different variation of this formula. We can say 1/2 mv squared is equal to force of friction times the displacement. Okay, and we know that the force of friction is equal to mu times the normal force times the displacement is equal to 1/2 mv squared. Wow, all the units are just coming together. All right. Okay, so what about this one? Here we said that the work here done was positive, so let's just prove that. We have the block. The block is moving to the right, okay? We have f of n, we have f of g, okay? But it's not moving in the same axis as the forces, therefore those two forces will not do work. But here we have a push. And here you can see that this velocity and this push are along the same axes, right? They're both in the x-axis, but more importantly, they're pointing in the same direction. So because they're pointing in the same direction, the the work will be positive. Okay, and we indicated that by showing that the energy goes into the system. Wowie zowie. I think that's it. Okay. In class, we'll talk about a lot of different niche cases, a lot of fun little scenarios about like when you're actually doing work, and the idea of like network overall. But until then, I'll see you later. Bye bye.